Let's talk about the complexities of atoms. I'm Eric Steinhardt, and you can learn more about me at ericsteinhardt.com. What we're doing here is applying the concept of complexity that comes from the work of Richard Dawkins. I recorded a previous video on that concept in particular, so now let's apply it. And we're going to ask a question here. It's a question that comes from Epicurus, and the question is nature random? Is he right? We want to use complexity to try to answer that question. He thought that nature is particles moving randomly in space. Is that right? So let's talk about complexity. This is the Dawkinsian concept of complexity. Things have varying degrees of complexity. Complexity is a property of types of things, not of particular things. And here we're focusing on types of atoms like hydrogen, helium, lithium, and so on, all the way out to uranium. Complexity. So atomic types are defined by protons, and we're going to focus on the protons. We can ignore neutrons and electrons. There are 7 steps in analyzing the complexity of something, and here they are. First, we break an atom down into its protons. We list all the arbitrary ways of reassembling the protons. Then we list all the ways that recover the original type of atom. We count the number of arbitrary ways. We count the number of recovery ways, ways to recover the original type. And we divide the arbitrary ways by the recovery ways, which are also the stable ways, the ways that preserve the type of the atom. And then we take the base 2 logarithm to get bits of complexity. Let's talk about the complexity of hydrogen. A hydrogen atom contains 1 proton, A. So the set of its proton parts is the set that just contains A. There's one way of arranging this part, so the arbitrary multiplicity is 1. And there's one way of making a hydrogen atom, given that 1 proton, so the stable multiplicity is 1. Okay, a little math. The complexity of hydrogen is, we have the raw complexity, which is the arbitrary multiplicity divided by the stable multiplicity. 1 divided by 1 is 1. And we take the base 2 logarithm to get complexity in bits. So the base 2 logarithm of 1 is 0, and that gives us 0 bits. That's the complexity of hydrogen. What about helium? Helium has 2 protons, A and B. The proton set's the set of A and B. There's 2 ways of arranging these protons. Either they're separated or they're joined. So the arbitrary multiplicity is going to be 2. 2 ways of arranging the protons. There's only one way that recovers the type helium, one way of making a helium atom. So the stable multiplicity is 1. This means the raw complexity of helium is the arbitrary multiplicity over the stable multiplicity. 2 over 1 is 2. So the complexity in bits is log 2 of base 2, 1 bit. Helium has 1 bit of complexity. What about lithium? Let's not do all that complicated stuff with sets. Let's just say a lithium atom has 3 protons, A, B, and C. They're colored. There are 5 ways of arranging them. There they are in that diagram. They're all separate, or they're all together, or you have pairs and 1 left out. 5 ways of arranging the protons, 5 arbitrary ways, right? Lithium atom has 3 protons. There's the set. There's 5 arbitrary ways of arranging them. So the arbitrary multiplicity is 5. But only that one way of combining them all together, sticking them all together, A, B, and C, is a lithium atom. So the stable multiplicity is 1. That's the way of recovering the type lithium from all the arrangements of protons. So the raw complexity of lithium is arbitrary multiplicity over stable. 5 over 1 is 5. The complexity of lithium is going to be the log 2 of the raw complexity. No need to worry about that here. What we do is talk about sets of parts when we're talking about complexity. The lithium atom is the set of protons A, B, and C, 3 different protons. And look at this arrangement where we stuck A and B together and had C separate. That arrangement is a way of partitioning the set A, B, C into its subsets A and B and C. So the arrangement that consists of A and B stuck together and C separate off to the side is a set of subsets, right? It's the set that contains the subset A and B and the subset C. Each arrangement of protons, given some set of protons, each arrangement is a set of subsets of that original set. Thinking of arrangements as sets of subsets helps us to count arrangements. That's why we do this exercise. And this leads us to the Bell numbers. The Bell numbers, the number of ways to arrange the parts in a whole with n parts, is the number of ways to partition a set with n members. A partition of a set distributes all of its members into distinct compartments. The compartments don't share any members in common. They're disjoint. How do we count partitions? The Bell numbers count the partitions of sets. The nth Bell number is the number of ways to partition a set with n members. Here are the first 10 Bell numbers. 1, 2, 3, 5 is the third Bell number, 15, 52, 203, 877, 4,140, 21,147, and 115,975. These numbers go up quick. We'll use the Bell numbers to talk about the complexity of beryllium. 4 protons, the fourth Bell number is 15, so there's 15 ways of arranging those protons, and there they are shown in that diagram. The arbitrary multiplicity, of beryllium is 15. One arrangement makes beryllium, so the raw complexity is 15. More complex atoms. The nth atomic type has n protons, so the number of arbitrary ways of arranging them is the nth Bell number. The arbitrary multiplicity is just the nth Bell number. Only one way makes an atom of the type, namely the one way in which all the protons are stuck together. So the stable multiplicity is always 1. That means the raw complexity of the nth atomic type is always the nth Bell number divided by 1, which is just the nth Bell number. Here we go. Here are the raw complexities of some atoms. The raw complexity of hydrogen, just the first Bell number, which is 1. Helium, 2. Lithium, 3. Beryllium is just the fourth Bell number, which is 15. Boron, 52. Carbon, 203. Look at these going up really fast through all the Bell numbers. By the time you get to phosphorus, that's huge, right? 1.3 billion ways to arrange the protons in a phosphorus atom. That's a lot of ways. Now let's go back to our question about the randomness of nature, talking about complexities and randomness. Is nature random? Epicurus thought that nature is particles moving randomly through space. Is he right? We can ask a question about atoms. Are complex atoms created randomly? More precisely, how likely is it that a random lottery creates a complex atom? Let's talk about atomic lotteries. There are atomic lotteries whose tickets are ways of arranging protons. The nth atomic lottery is a bucket filled with tickets. Each ticket in the nth atomic lottery is a way of arranging n protons. So the number of tickets in the nth atomic lottery is the nth Bell number, and only one of those tickets is a winner that makes an atom of the nth type. Here's the Phosphorus Lottery. Phosphorus has 15 protons, so the Phosphorus Lottery is a bucket filled with tickets. Each ticket is a way of arranging 15 protons. The 15th Bell number is 1.38 billion, so there's 1.38 billion tickets in the phosphorus bucket. Over 1 billion tickets in the Phosphorus Lottery, and only one ticket is a winner. So the odds of drawing the winning phosphorus ticket are less than 1 in 1 billion. One ticket makes a phosphorus atom, that's the winning ticket. The odds of drawing the winning ticket, less than 1 in 1 billion. Now a lottery is a random process. So the odds of getting a phosphorus atom in a random process are less than 1 in 1 billion. The odds of a phosphorus atom appearing by chance through random collisions of protons are less than 1 in 1 billion. And that means phosphorus is extremely unlikely to appear by chance. So we have chance versus complexity. Complex things are extremely unlikely to emerge in random processes. The probability of complex things emerging by chance very rapidly vanishes. It drops towards 0. Complex things require non-random processes. Nature is filled with complexity, and this entails that nature is extremely non-random. Processes in nature are extremely skewed away from randomness. Nature is not random. Epicurus thought nature is particles moving randomly in space, and Epicurus was wrong. Nature is not matter in random motion. Matter does not move randomly. Nature is not random. And Dawkins knows that complexity does not come from chance. Dawkins stresses this over and over again throughout his books. Complexity cannot arise from chance. But what's the alternative? The alternative is nature self-organizes. Of course, the alternative is evolution. But let's talk about self-organization and think about Nietzsche for a minute. Nietzsche thought of nature as self-organizing. Nature is a self-creating work of art. Epicurus is wrong, Nietzsche is right. Thanks. That's me, Eric Steinhardt, Professor of Philosophy at William Patterson University. You can learn more about me at www.ericsteinhardt.com. This is a series of videos examining themes of complexity, randomness, organization in the work of Richard Dawkins and other authors. Thanks.